Thank you. Thank you for the kind introduction. I'll be presenting today some of the work we do in my group on responsive and disordered porous frameworks and the way that we can use computational tools to model these systems and the phenomena that occur. I want to thank the organizer for switching the MOF 2020 conference online and allowing so many participants and have such a broad reach. And I think it's really good way of connecting. Of course, we're all missing the traditional conferences, but there are upsides to web conferences, and easier access for everyone is really good. So I'll be discussing a bit then the work done in my group in Paris. And as any colleague who has visited my flat can tell you, I love disorder. This is why actually there is a background picture of Paris and not the view from my home, because I love disorder too much. And it's the same for materials. I'll be discussing today a subclass of metal-organic frameworks. I don't need to introduce what MOFs are, of course, in this conference. The interest I have in these materials is especially focused on their high structural flexibility and the fact that this is both an advantage and can also be a limitation for applications in some cases, as we will see. And so it's this particular phenomenon that is of interest to me. And I'm using the terminology introduced just earlier this afternoon by Professor Kitagawa of soft porous crystals, because I think it's important to focus on the fact that any supramolecular structure, any chemical structure possesses some flexibility. So all materials are flexible. It's just that some of them have different properties and the transformability of their structure that allow them to have large-scale transformation between well-defined states, and in most cases, reversible transformations between these states. And so the terminology of soft porous crystals, which you'll hear me use in the following, is really focusing on that particular class of materials. And these soft porous crystals, they can respond to a lot of different stimulations from their environment. It can be change in temperature, the application of pressure, whether it's isotropic or anisotropic. It can be adsorption of gas molecules in the fluid or in the, in the gas or in the liquid phase. It can be light, electric field, etc. You can imagine any physical or chemical stimulation to these soft porous crystals, and they will react to it. What we try to do in my group is to understand, as part usually of collaborative work with many different experimental groups, we try to understand the behavior of these systems by using a computational toolbox of different methods that allow us to have a more complete picture by studying the systems. And I know that Tina Duren yesterday already introduced the basic concept of molecular simulation. So I'm not going to do it again, and I'll try to focus this talk on results, systems, and phenomena, rather than on methods and equations. But you can ask any question, or you can contact me after or read the papers to have details on the computational methods. But what we try to do shortly is to study this system and this phenomena at different scales. So at the smaller large time scale and smaller length scale, we look at the structure and energetics of the materials with quantum chemistry calculations. Then we deform them slightly, studying their vibrations and their elastic deformation in harmonic approximation and elastic approximation of their mechanical properties, still at the quantum chemical level. And this is slightly already going to a little bit of a larger length scale. Then we can look at local dynamics, so rotations of molecules, molecular rotors inside MOFs. We can look at the flipping of rings. We can look at the stretching of bonds, even outside the harmonic approximation. We do this with ab initio molecular dynamics. So we start looking at dynamics on the scale of picoseconds to maybe tens or hundreds of picoseconds. If we want to study longer time scales, we go to dynamics with parameterized classical molecular dynamics. And then we can address problems of diffusion and molecular transport inside the materials. We can study rare events, and we can do simulations that can go up to more than thousands of atoms and several nanoseconds or dozens of nanoseconds in time scales. So we study bigger systems, larger time scales, but with lower accuracy or lower transferability of the method. We need to create a new force field for every specific systems, basically. And we can go even higher in terms of length scales and look at thermodynamics of this system. So the equilibrium between different phases using Monte Carlo methods, analytical models, and etc. So, and the approach from my group is using these different theoretical tools to try and obtain several points of view on the same system to actually have a good picture of what's happening. And I'll give examples of that in the following. If we look at the thermodynamics of flexible systems, and in particular soft porous crystals, which present porosity, it's in the name, so there can be adsorption of fluids. Basically, it's a system that can deform, so a given amount of matter that can deform under certain conditions of pressure and temperature, and it can exchange molecules with the outside. That's the open nature of the system that allows for adsorption to occur. So basically, it's in equilibrium with an outside reservoir of fluid. And the systems like that, they're described in thermodynamics and in statistical thermodynamics by what's the so-called osmotic ensemble, where the volume of the system, the amount of molecules adsorbed can all vary. We can study these systems directly through simulations, such as Monte Carlo simulation, and Tina Duran gave examples of that in her talk. We can also make thermodynamic models based on analytical theories of these systems. For example, using the thermodynamics equation and mixing them with phenomenological descriptions of adsorption, such as isotherm models, such as the Langmuir isotherm, for example, we can create thermodynamic models that allow us to understand the behavior of these systems as a function of key parameters. And the key parameters are thermodynamic variable: pressure, temperature, gas pressure, gas composition, or chemical potential, which is equivalent, etc. And we can understand the systems by drawing, for example, phase diagram. Here is an example of a phase diagram of a MIL53 material that is a bistable material with two different phases, and you can rationalize its behavior by looking at how it changes as a function of temperature, of gas pressure. And you can see that it's a nonlinear behavior, so it's something that's a bit puzzling from the experimental point of view if you were to just look at constant pressure or constant temperature curves. So you really need to explore the parameter space of this system. On the right, you have the same system with different gases, xenon, CO2, and methane, and you can see that the nature of the guest molecule, of course, influences the phase diagram of the system because the host-guest interactions are going to be different. And so now we have another variable. We've taken our two-dimensional phase diagram and we're making it 3- or 4-dimensional by introducing composition of the gas mixture with 2 or more components. And we can create thermodynamic models and theories to understand that, to rationalize experiments and to make predictions. So this shows one of the ways that the models can be used, the theoretical models, analytical models, can be used to better understand and predict the behavior of materials and of soft porous crystals in particular. They allow us to explore a wide parameter space that would be experimentally very difficult to explore systematically. So we can calibrate thermodynamic models based on a few experimental data points, and then make predictions, understand the behavior, and if we find something interesting, we're going to go back and test it and continue the loop of discovery and understanding of these materials and phenomena. So it's really integrated with experimental work. So that's the thermodynamics view of flexible materials, and I won't focus much on that today, but there is another view of the same phenomenon, which is also very interesting. And it's the fact that if you look at these flexible systems and adsorption in flexible systems from another point of view, you can see it as not a thermodynamic process, but a mechanical process this time. The material open, and here it's a picture of MIL53, so again, a bistable material. So the metal organic framework starts in a given state, and as you start to adsorb molecules inside, these molecules interact with the framework and they create a stress on the framework by their interactions. Where there is energy, there is force. So that force propagates on the whole framework to create a pressure, basically. And that means that you can actually, in the same, interpret these transitions of metal organic frameworks, of soft porous crystals, as a function of adsorption. You can interpret them as being driven by mechanical pressure, which is due to the stress of adsorption. And this is interesting because this allows you to connect the behavior under adsorption with the behavior of the system under pure mechanical pressure. And the behavior of MOFs under pressure is something that's been quite studied and that is very, very varied. I mean, the different types of MOF responses to application of pressure is huge. Some of this system can undergo single crystal to single crystal phase transitions. Some of this system can undergo bond rearrangement. This is an example from the Cheatham group. Some of these systems can undergo amorphization through compression or through ball milling, and some of them undergo very varied linear responses, such as negative linear compressibility or low shear modulus. So there is really a broad range of different responses of materials to pressure. And then it's interesting to see what we can do as theorists, what methods we can apply to understand these responses to pressure. So at the smaller scale, at the smaller length scale, what we can look at is how these materials react to small deformation. So we're going to look at the elastic behavior of flexible MOFs. Now, the elastic behavior of materials is dictated by their elastic tensor. It's a 4-Frank tensor that's represented here. It's basically the response of the material to the deformation. The tensor itself is a mathematical object. We can calculate it from quantum chemistry calculation by applying different strains to the material and seeing how it reacts. But more importantly, we can, from this elastic tensor, once we have calculated it, extract physical properties that are meaningful to us, such as the Young's modulus, the shear modulus, the linear compressibility, the bulk modulus, etc. And so these we have intuition about this. They have more meaning to us than the elastic tensor. So they're the ones that we're gonna look at. For example, I take the Young's modulus. So the Young's modulus is the response of a material under compression along one axis and one axis only. So if you take two different MOFs, MIL53 on the right, this wine rack type framework, which I've shown a couple of times now already, and ZIF8 on the left, which, at least for the mechanical properties, can be considered rather rigid in a limited range of pressure. If you look at the difference in Young's modulus of these two materials as a function of direction, where do you apply the pressure, you can see that there is a lot of difference. All crystals are anisotropic by nature, but some are more anisotropic than others, and MIL53 has two orders of magnitude between the soft directions, which are the axes of the wine rack here and here, and the stiff directions, which are typically along the linkers. I hope you can see my hands. And so there are two orders of magnitude difference in the stiffness of these directions, which mean that It's sort of a signature of the flexibility. The material has inherent soft deformation modes. And in fact, we can expand that to other materials and other soft porous crystals, and we found that it's quite systematic. And so looking at the elastic properties allows you to find the signature of the potential for flexibility of these frameworks. And we did it for a number of materials since then, so that we have even more data. You can find, of course, other properties such as negative linear compressibility, which is rather common actually in framework materials because of the way that they're built. But it actually occurs in the MIL53 family and was experimentally confirmed by the group of Rohe Gascon. So that's how we can use a computational tool to understand the behavior of these systems at the relatively small length scale. Can we go bigger? Can we go to larger length scale? Well, one of the systems that we've studied in the group in the past is the DUT49, and this is part of a collaboration with the group of Stefan Kaskel in Dresden. And so this DUT49 material has flexibility, which I'll detail in a moment, but it's flexibility that cannot be described in the elastic regime. We tried and we showed that it doesn't work. It's not an elastic phenomenon. It's something that happens with larger scales of deformation. So what happens? Well, this highly porous, ultra high porosity material, actually based on copper, actually has a weird step in its methane adsorption isotherm at 111K. And this phenomenon has been called negative gas adsorption. It's basically that the materials expels gas as the pressure is increased instead of adsorbing, which is quite unusual, which is actually forbidden under the laws of thermodynamics at equilibrium. So it already tells us that it is something to do with non-equilibrium phenomenon. And we try to understand how that happens. So if you look at the change in the structure, you can see that there's a very high change in the volume in a cubic to cubic transition. And we already get the idea here that the transition is of very large scale. So that's one element of an answer to the question of why we don't see it actually in elastic calculation, in calculation of the elastic properties. And this transformation is linked to the bending of this biphenyl unit in the linker, as you can see on the left of the screen. And this is actually quite energetically, there's a high price to pay to do that. And it appears that the adsorption is allowed, the phenomenon of adsorption is sufficient to pay that energetic price and drive the transition. And that's because the absorption in the denser form is favorable over the large pore form, because the molecules that adsorb inside the material, they have stronger interactions. Now, this is not enough to explain why the system actually closes down, and why, when it does so, it expels gas molecules. So the system has to be outside of equilibrium to do so. And without going into detail, we can write thermodynamic models to understand that. But what we really wanted to do was to look at why this happens at the really microscopic scale. And this is something that was done, a study that was done in my group by Jack Evans, now in Dresden. And the idea was to look at the behavior of this biphenyl unit and show that if you compress it, and this is really like an in situ experiment of compressing in the computer the ligand molecule by taking the two nitrogens and applying, applying constraints to them. If you do that, you will see that the first, for small deformation, the system is rather stiff and it does not want to deform. And then once you reach a certain amount, of constraint, then you're going to see buckling. And the buckling is similar to that which is seen in textbook for steel bars of 1 meter in length. So it's a very macroscopic phenomenon that is also occurring at this very small scale. And the buckling means that once you've started to break the symmetry and go out of the plane, and bending the linker, then it will go basically all the way, because there is no stiffness left in it. And so this allows us to understand, putting all these pieces together, the ligand buckling, the driving force, which is the adsorption of the gas, the metastability, which is indicated by the thermodynamics model and which is related to the buckling of the linker. This is putting together all the pieces at the different scales that allow us to provide a full understanding of this system. And actually, it ties with also experimental data at the various scale, crystallographic data, and adsorption data at the macroscopic scale, and even further characterization techniques through spectroscopy, etc. So we can really only have a complete view of this system and a complete understanding of the system with these various techniques, experimental and computational, that are looking at different lengths and time scales. We could actually, and I'm not talking about it today, I just wanted to give the basics on that, but we can actually go further, and Jack Evans and Simon Krause and others have continued looking at the systems and going further in understanding how you can tune the phenomenon, and continuing to make very nice links between the microscopic and macroscopic behavior of these systems. Now, I've talked for now of flexible materials, of soft porous crystals, and the way that we can describe their flexibility and their response to stimulation. It happens that one of the things that gives rise to their flexibility is the high dimensional nature of the frameworks, with a lot of degrees of freedom, most of them associated, well, some of them associated with relatively weak interactions. And this allows, this is what creates the entropy necessary for flexibility to occur. But in metal organic frameworks and in soft porous crystal in general, there are other phenomena that come from the high dimensionality of the supramolecular assembly. And these are the presence of defects, not always, but often, and the possibility for disordered state to appear. And these are all linked, and it's part of the directions of research in my group that we've been trying to go and look at this. And so now, having said a few things about flexibility, I'm going to focus on the other aspects of this, which is the creation of states and the understanding of the disordered states, which can be linked to defects. And this work started by trying to understand the presence of defects in UIO66. UIO66 is one of the first MOF that was widely realized to present to be able to present a significant amount of defects, depending on the synthesis conditions and the activation conditions. And the group of Andrew Goodwin showed that you can actually tune the concentration of defect with the synthesis conditions. And they further studied this, and we collaborated on that topic to understand how these defects are distributed inside the material, because most of the work dealing with defects in metal organic frameworks assumes that they're randomly distributed, because, well, basically because if you don't have any other information, that's the most reasonable thing to assume. Just like if you have a mixed metal MOF, unless you have specific information, you're going to assume that the metals are randomly distributed. Well, it turns out that in the case of UIO66, that's not really the case. And the defects, they don't distribute randomly, but they create nanodomains of defective phases within the bulk of the crystal, where you have areas of pristine UiO66 and areas of the defective phase. And you can very clearly see on the lower left the domains that are being created in these electron microscopy images. So these defective phases, under-coordinated phases, they're actually, they have different properties. And this is why it's really important, even beyond the fundamental understanding, to understand the disorder, or correlated disorder in this case, induced by the presence of defect. It's because it's going to impact the properties of the material and impact them very strongly. We looked, for example, at the thermal expansion of the defective UiO66, and it's very different from what you would have in a defect-free UiO66, and it's also very different from what you would have with randomly distributed defects, because the mechanism by which this very large negative thermal expansion occurs is linked to the presence of this these nanodomains of defective phase. So we really need to understand the behavior of these disordered phases in metal organic frameworks. Another area of properties that is directly affected by the presence of defects and by their distribution is the mechanical stability of the systems. And many MOFs are actually, UiO66 has very, very good mechanical stability. It's rather a stiff material, but the mechanical stability can be a limitation in application of a number of MOFs. So understanding what can improve or degrade mechanical stability is really a key issue in designing new materials, or understanding the ones we already know how to synthesize. And so we've been able to show, and this was a collaboration with Aaron Thornton, Cyro, that the presence of defects and their distribution directly impacts both the porosity of the materials, as you would expect, and the mechanical stability as well. So that basically you need to have a compromise in this system. If you introduce defect, you can create more porosity, but you degrade potentially the stability of the system. So we can already see how defects and disorder affecting different properties of the system might make some of them more, more desirable, and others might be degraded, so that you need to reach a compromise. In this same line of research, the group of Shane Telfer has been designing very nice multi-component MOFs, which they call defect-tolerant MOFs, for a reason you're going to see in a minute. And they're MOFs based on zinc with 3 different types of linkers, so they are quaternary MOFs. And if you synthesize the MOF32, which is highlighted here in red, then it has a structure where basically the network topology features some redundant connections that you can remove without losing connectivity of the system. And so basically, of the 3 types of linkers, 2 can be removed in large proportions, so you create defects, but without significantly reducing the stability of the system. And the Telfer group was able to show that this actually directly affects CO2 uptake, nitrogen uptake, and so you can tune, you have a family of systems where the behavior, the adsorption behavior is tunable by the different proportion of linkers, while retaining the same parent framework and retaining the stability of the system. So this is sort of improving on the situation by having redundancy built inside the material. Now, I've discussed a bit these disordered systems, and I think if we're going to talk about disordered systems, then the most you know, the ultimate disorder in a solid is the liquid state. I'm fully aware this is a very weird and controversial statement, but yeah. So if you hit these metal organic frameworks, Tom Bennett and his group showed that in some cases that you can actually obtain liquid metal organic frameworks, and we've been collaborating now for a couple of years to try and understand the mechanism of melting, the properties of the liquid MOFs, etc. So you start from a porous ZIF, you heat it up, and there is a sweet spot between the melting temperature and the decomposition temperature. You have a window where you can operate and when you can obtain a liquid MOF. We've been using here ab initio molecular dynamics to study these systems because classical methods are not suitable. They wouldn't be able to reproduce the bond breaking phenomenon of the zinc imidazolate coordination being broken. So these are quite expensive computational methods, but they allow you to simulate without any kind of model or assumptions about the nature of the interactions. They allow you to simulate the behavior of these systems and actually look at the melting of the system as you increase the temperature. And so you can, from these, from this ab initio molecular dynamics, obtain microscopic structures and radial distribution functions and coordination numbers and potential of mean force along certain distances, and even look at the mechanism as a little movie that you can play over for how this coordination is broken and how typically the zinc imidazolate coordination is replaced from one by a linker exchange event, basically. So this is very useful because obtaining direct experimental information in situ on these systems at high temperature and possibly high pressure, as we'll show in a minute, is quite difficult. And obtaining microscopic information, for example, spectroscopic information, is often a bit indirect, and you get things like, you know, total pair distribution functions, but they're not always trivial to interpret. So the simulations here give us an additional way to look at the system at the microscopic scale. So in the case of the melting of ZIFs, we've been able to show that it happens through under coordination of the zinc linker with a significant of the zinc metal, sorry, with a significant number of zinc atoms moving towards threefold coordination, which allows the system to have some dynamics and to actually free diffusion of the linker and metals. And of course, you can do that under pressure, you can do that at high temperature, and we've continued to work on this. I won't give any details there. We've continued to work on this to try and understand the difference between, you know, high pressure, high temperature phases. And experimentally, it is possible to obtain different amorphous phases from this system by going to the liquid phase and cooling it down. By quenching, or by going to high pressure. In simulations, it's a bit harder because all the methods I've described above, they're able to deal with systems of a few hundred atoms in terms of length scales. And beyond that, everything is too expensive for us to compute. Yet, disordered phases, amorphous phases, they involve no long-range order. And so in order to describe them computationally, we would need to simulate bigger systems. And those are too expensive. So how do we do? Well, it's a bit difficult, but we try anyway. And one of the tricks we can use is actually to do replicas of the system and do the simulations many, many times on different replicas. And so we've been very recently publishing our first paper on understanding the structure of ZIF glasses, ring statistics, force volumes, coordination number distributions, by doing simulations of actual melting and quenching of ZIF, starting from the crystalline phase all in the computer, which is very expensive, and we have to do it many times in order to, for example, for the quenching, in order to get different structures and average over those in order to mimic what would in effect be a macroscopic sample of a glass and its large distribution of different structural properties. So I think this is a first step, and we've shown that it's possible, expensive but possible, and now it opens the way to actually modeling MOF glasses on a larger scale and trying to understand their properties better. So right now we've focused on structural properties, but we can look at other properties, electronic properties, etc. Finally, I want to conclude this on, it is not really a result, it's more of an opening and something that I think should be a good perspective for the future. And the idea comes from a collaboration with the Andrew Goodwin's group in Oxford on gold and silver cyanide that shows that you can create complex structure by frustration. If you take gold and silver cyanides, their structure is relatively easy. They're made of 1D metal cyanide chains that are vertical in all my pictures. And these chains are packed in the plane to make the full material. Gold cyanide packs in the way that all the gold atoms are on the same plane, and silver cyanide packs, the chains pack in a bit weird way where they're all shifted next to one another. And this has been well known for a long time. If we want to understand why, well, we can look at the energy difference, at the evolution of the energy of two chains, just two chains next to each other as we shift them a little bit. And when we do that, we get the energy profiles that are featured here. And we find that because gold likes to be next to gold, because of orophilic interactions and the D10 orbitals of gold. So basically, because gold likes to be next to gold, the system has all the gold planes, all the gold atoms in the same plane. On the other way, silver doesn't have so much argentophilic interaction, so silver plus likes to be next to the cyanide minus, so they like to be shifted by half the silver chains. But if you're packing them on a triangular lattice, as is shown on the right, you cannot have every chain shifted by half because there are three. In a triangle, there are three. So if you shift one by half, the other one has no choice left. So what happens is that the final configuration is created by some sort of frustration already that shifts by 1/3 each of them, which is, you know, it's not 1/3 is not half, but it's better than 0 apparently. Okay, now the smart idea of the Goodwin group was to think what happens if you do mixed cyanide chains, half silver, half gold, and they're actually they're well localized. So you have one gold, one silver, one gold, one silver, etc. Because then you have the combination of the effects. Gold likes to be next to gold, but silver would prefer to be next to the cyanide. So the free energy profile, which you can see in the C panel over there on the right, is actually a lot more complex. And what happens is that when you want to pack these systems on the triangular lattice, now the energy is not just ferromagnetic or anti-ferromagnetic, it has a coupling of a higher order. And so the system is creating some sort of state that is locally anti-ferromagnetic, but with a larger, you know, a larger length scale order. And this is this is called ferroquadrupolar state, and it's represented at the bottom. And I won't go into the detail of it, but the idea that you can see here is that you're creating new structure and new properties by frustration based on the building blocks that you put. It's a bit like having your kids play with Lego bricks, but not giving them exactly the right type of Lego bricks that would fit to make the easy choice, giving them weird shapes that don't really fit together. And they still have to make a structure out of it. And you can think that it's going to be more complex than just fitting all the square bricks on top of each other. And hopefully, they will like the structure that they create, and it will be more interesting than just the lowest symmetry structure. So, and I think, so I wanted to give this example because this comes from a different field. This is cyanides, it's not MOFs, but I think we can extend this idea and actually use it to create novel phases. And I won't talk about it in detail. It was published, there was a preprint published on ChemArchive this morning on skyrmionic phases of MOFs. Again, a collaboration with the Goodwin group. And I think we can create phases like that by engineering the interactions at the microscopic scale, and these phases will have new properties. Now I want to end with thanking my institutions that sponsor my work, collaborators on the experimental and theoretical sides. I thank you for your attention.